Hello students, my name is Shashank Shekhar and we'll today start the fourth lecture of the chapter, that is Haloalkane and Haloarene. So in the previous class, we have completed this preparation of this haloalkanes. Today I will just show you one more preparation which is kind of important, because in the previous lecture, if you have seen, we have only prepared chlorine, bromine and iodine related alkyl halides, but we have not seen any method that is applicable for the preparation of fluorides or alkyl fluorides, I would say. So for that I will give you one reaction, and after that we will move to the physical properties of the haloalkanes and give an introduction of this chemical reaction related to it. So today we will mainly focus on our physical properties of this haloalkane. So if you look at the syllabus, so we are done with this part. So today we are starting with this one. Okay, so today we'll see the physical properties, right? And if you look here, these are the topics that we will cover today. So I will cover the last of this preparation, that is halogen exchange. We will try to see that how can we prepare alkyl fluorides using our halogen exchange process. After that we will move to physical properties, in which we will see boiling points, density and solubility. Also we have one illustration of this boiling point, that whether the generalization we are putting upon is right or wrong. Then we will just see an introductory part of this chemical reaction, that is what type of chemical reaction can be happening, means classification of these types of chemical reaction. And we will see an introductory part of this nucleophilic substitution. Okay, so first of all, let us start with the halogen exchange. So halogen exchange means, if you see the term, you will be able to say, get the first idea that we are exchanging two halogens. Okay, so what we are doing, we are exchanging two halogens. Now for that, two reactions are very popular. In case of alkyl halides, we have two reactions. The first one is Finkelstein and the second one is Schwarz reaction. Okay, Finkelstein and Schwarz reaction. Now Finkelstein is used for the preparation of iodides and Schwarz reaction is used for the preparation of fluorides. So I would say that this is the only method that we have studied, that is the Schwarz reaction, that can be used to prepare fluorides. So we are not directly preparing alkyl halide in this halogen exchange process. First we prepare an alkyl halide and then we replace with another halogen to get our required alkyl halide. So if I talk about the Finkelstein, which I have told that we use it to prepare alkyl halide. So if you want to remember it, so children get confused that which halogen exchange is for iodine and which halogen exchange is for fluorine. So Finkelstein, so if you just look at this word, you can get an I pronunciation at the last. So you can try to remember using this. So I have used this trick and I think it works far better. But if you have any of yours, you can keep it with, you can go with it. But if you don't have any trick and you get confused between this Finkelstein and then Schwarz, just remember that this Finkelstein is ending with an ion sign, so it is for iodine. Okay, so this is just a trick to remember your reaction. So a student may think that, okay, it is bad to remember reactions. Okay, and I would say that it is a bad practice. It is not a very good practice to remember something, or to you can say I would say that to remember something is not that much appropriate. But from exam point of view, since you have to qualify your exam, you have to do certain things which you think maybe is not a good practice. Okay, so it is okay for some time. It is okay to have this type of tricks to go through your exams properly. That would be worth it. Okay, so similarly you can use here that Finkelstein ends with the ion sound, therefore it will be iodine. Okay, this is for use for the preparation of iodine. So what do we do here? We take sodium iodide in dry acetone. Sodium iodide in dry acetone and react it with the hydrogen halide. Then we get our alkyl iodide and NaX. And what are the X? What can be the X here? It can be chlorine, either chlorine, or it can be either bromine. So at last we are getting our alkyl iodide. Now one more thing, this NaCl and NaBr are formed, is precipitated in dry acetone, and it facilitates the formation of forward reaction according to Leach-Arterial principle. So since this NaCl and NaBr, you must be very sure about it that it is an ionic compound, and since it is an ionic compound, it is polar in nature and it is not soluble in dry acetone. Okay, as compared to NaI, because this NaI here is not that much polar, because it has less ionic character as compared to NaCl and NaBr due to Fajan's rule. If you remember the Fajan's rule, you can think of it that larger the size of this anion, greater is the covalent character. So here iodine is of the largest size, so it will have the greatest covalent character, and hence it will be less polar as compared to NaCl and NaBr. Now as soon as this reaction starts and we started the formation of this NaCl and NaBr, that is sodium chloride and sodium bromide, they start to precipitate, and due to precipitate they get out of the solution mixture where the reaction was happening, Now due to this reason, the reactant has been removed, or you can say a change has been made to this equilibrium. Now if you invoke this Leach-Arterial principle that says that if you do something to an equilibrium, or you apply some external methods to this equilibrium, then the reaction will proceed in such a way that the change effect can be minimized or can be brought to minimum. So you have removed the product. What we have done, that due to precipitation of this NaCl and NaBr, we are kind of removing our this reactive product. How is this different from the reaction mixture? Because we are getting it as in the form of precipitate, and precipitate is not present in the reaction mixture, so it gets out. Okay, it gets precipitated out. Now we have less products, so according to Leach-Arterial principle, the reaction will proceed in forward direction so that this equilibrium can be established again. So in this way you can say that we are using this removal of sodium halogen, that is sodium chloride and sodium bromide, to facilitate our reaction at a much faster rate and get a greater yield. Okay, now the next is Schwarz reaction. So this is the only reaction, this Schwarz reaction is the only reaction that can be used to say prepare our fluorides. Okay, so if you remember all the preparation methods before, you have read before, you must have not seen this preparation of fluorides. And I would say there is no direct method. I would not say no, means I would say that in this discussion or in this syllabus, there is no direct method of preparation of this alkyl fluorides, but we can do it indirectly. If you just look here, we have exchanged this our bromine with fluorine, so we can do it indirectly by using halogen exchange method. So the synthesis of alkyl fluorides is best accomplished by heating alkyl chlorides or bromides in the presence of metallic fluorides like AgF, Hg2F2, CuF2 and SpF3. Now I want to make a point here that students try to remember all of this reagent. Suppose you have just remembered this equation, okay, and in the exam you got this reagent in place of this. Okay, so suppose this reagent was placed in this, then student gets confused and say, okay, so this is out of syllabus. So do not get confused in that way. It is within your syllabus. We have just changed a different, you have just used a different reagent that has the same properties in this reaction as this AgF, or we can use cobalt fluoride, or we can use antimony fluoride. So 4 fluorides are possible: Ag, Hg, Co and Sb. So all of these metals, fluorides, give the halogen exchange reaction, that is the Schwarz reaction. Therefore, we can use it for the preparation of fluoride. So at last we get methyl fluoride, and again this AgBr is formed. Okay, this is a simple ionic reaction. You can imagine it very clearly that this fluorine is substituting this Br. Okay, so we'll see the types of reaction, the substitution reaction not, but you can see the how this reaction is going easily. And we are using fluorides like fluorides of silver, fluorides of mercury, fluorides of cobalt, and fluorides of antimony to prepare our alkyl fluorides. Okay, so remember all these names. If you want, just make a small shortcut for it, or you can remember it like this only, then remember it. So this was this were the two important halogen exchange method through which we can prepare our alkyl halide. The first one is Finkelstein, which help in preparing alkyl iodide. Okay, and this Schwarz reaction is helping us in preparing fluorides. Now next we'll move to some physical properties of this haloalkane. So we'll start with the boiling point. So methyl chloride, methyl bromide, ethyl chloride, and all of these are gases at room temperature. So all this lower molecular mass containing our alkyl fluorides, they're all gaseous at room temperature. Higher member of this group are solids or liquids. Okay, so if I talk about methyl bromide, then we will go to this ethyl bromide. So methyl chloride and methyl bromide and ethyl chloride, all of these are gaseous in room temperature. Now if we move to higher member, that is ethyl chloride or ethyl bromide or propenyl chloride, then they can be solids or gas both. Okay, they can be solids or gas both. Due to greater polarity as well as higher molecular mass as compared to the parent hydrocarbon, so this alkyl halide have a generally higher boiling point. Okay, so what is the reason behind it? First of all, due to the removal of hydrogen and insertion of this halogen, we have increased the molar mass, and increased molar mass means our greater van der Waals forces. At the same time, we have introduced polarity, because initially carbon and hydrogen were not that much polar, creating not that much polar bond due to less difference in electronegativity. But as soon as we replace it with this halogen, which is kind of very electronegative, this will create a greater electronegativity difference, and we will get more ionic character. Okay, more ionic character. I will not say that it will become ionic in nature. It will have more ionic character. Okay, therefore it will be stronger and it will have a greater boiling point than the normal hydrocarbon. Is this clear? Okay. Now, for those who have not studied about this van der Waals force, so they are basically, so I would say only one statement. So this van der Waals force strength is directly proportional to the molecular mass. Keep this definition in mind. Keep this, or you can say keep this point in mind always, that the van der Waals force is directly proportional to the number of to the mass of the atom, or you can say molecular mass. And one more thing, that is the surface area. So as the surface area increases or the molar mass increases, this van der Waals force increases. Now due to this reason, chlorides, bromide, this is there are two reasons. So first is the intermolecular force of attraction. That would be either dipole-dipole interaction or van der Waals. Okay, so two type of interaction. Due to these two interaction, they have higher, say, our boiling point as compared to the corresponding hydrocarbon. The same thing is written here. This is why the boiling point of chlorides, bromides and iodides are considerably higher than those of the hydrocarbons of comparable molecular mass. So you should remember this. So if you have a hydrocarbon that has a very large molecular mass, then it will have a higher boiling point. Suppose it has 40 carbons and you are comparing it with this methyl chloride, methyl fluoride, then that 20 carbon will be having a greater mass and hence a greater van der Waals force, due to which it will have a higher boiling point. But if we see the comparison between almost, you can say, corresponding haloalkane and alkyl, haloalkane and your alkane, then you will see that haloalkane will have a greater boiling point due to dipole-dipole interaction and van der Waals interaction. Now this attraction gets stronger as the molecule gets bigger and bigger. So this should be always kept in mind, that as the size increases, this van der Waals force also increases. For the same alkyl group, the boiling point is this. Okay. So we are having the R same for all of this. Then we can see that this is the order of the boiling point. So you should remember this also. This is very important. Okay. This is very important. Is this clear? Now next is, this is because with the increase in size and mass of the halogen atom, the magnitude of our van der Waals force increases. Same thing is written here, that since we are using this halogen atom, there has a greater magnitude of size. Therefore, it will have a greater magnitude of van der Waals force, and its van der Waals force will increase. So if you see here, we have put a graphical representation of how, with respect to molecular mass, the boiling point changes. First of all, methane. So since methane is the first member of this alkyl halide, therefore the chlorides and bromides are gaseous in nature. Okay, but iodides are solid in nature. Okay, this is clear. So I mean here that solid or liquid, it can be any two of these. So due to the smaller molar mass of this CH3X, we are having a gaseous type of structure, or you can say due to less van der Waals forces. Therefore, chlorides and bromides are gaseous at room temperature. Further, iodides are not so because of the greater van der Waals force. Then next we have this ethyl. So in ethyl only we have this chloride present as our gases. Other two are present as liquids or solids. That is bromides or iodides. Similarly, if we introduce 3 carbon, then all of this will have the same state. Not same state, either solid or liquid. They will not be present as gas. So either chlorine, bromine and iodine. You can consider any 3 of them. Any one of them. Okay. So is this clear? So this was about the boiling point. Now we'll see illustration that how does this work. So we have 3 type of structures. They are all isomers of each other. I mean here that they all have same molar mass. So in case of same molar mass, we have to see the structure of that, say, isomer, or all of the 3 isomers. So the first one is methane, ethane, propane, butane. That is you can say bromide, butane bromide. Okay. Next is this bromide butane. Okay, but it is not this normal butane. It is our, say, this is our 1 2 3. So you can say 3 bromide butane. Then here we have the tertiary butyl bromide. Okay, tertiary butyl bromide. Now all of these have the same molar mass, almost you can say same molar mass. There's not that much difference in all of these, but these are not the molar masses. Okay, so they have the same molar mass, because the number of carbon is 4, and here it is also 4, and here it is also 4. 1 bromine, 1 bromine, 1 bromine. If you count the hydrogen, we have 3 plus 2 plus 2 plus 2, that is 9. Here also 3 plus 2 is 5, 6, 7, 8, 9, and here also 3 plus 3 plus 3, 9. So you can see that they have the same number of atoms, so they will have the same molar mass. But what is the difficulty here? Why are they having different boiling points? So the next factor that is to be discussed is this surface area. So the one which has a greater surface area will have a greater boiling point. So this is also a addition factor to our, say this, our van der Waals force. Or you can say it in a chemical way, I will say chemistry way, that more is the branching, less is the boiling point because of the decreased surface area, and decreased surface area results in less van der Waals forces. So this one has the maximum amount of branching. This one has this one is in the middle core, and this is the least one. So the least branched one has the highest boiling point. Then we have this 364, and then we have this 346. Okay, so this is our boiling point. Out of this, out of all of this 2-bromo-2-methyl propane has the lowest boiling point, where 1-bromo-butane has the highest one, and 2-bromo-butane has is in the middle one. Okay, this is clear. Now next, this is isobutane. Next we are the density. So the bromo, iodo, and polychloro derivative of hydrocarbons are heavier than water. The density increases with increase in number of carbon atoms, halogen atoms, and atomic mass of the halogen. Therefore, they have a greater density. So here is the density that is given. Only this one has our lower density than water, that is C3H7Cl. Keeping aside all of those, so if I talk about this bromine and chlorine, so all this compounds, or you can say derivative of this alkyl bromide and alkyl iodide, are heavier than water, and they have a greater density. So you should remember this thing, that bromides, alkyl bromides, and alkyl iodides have greater density than water. And polychloro compound derivative. Polychloro means more than one chlorine. The compound which has more than one chlorine will have a greater density than water. So it is written here, the density of all of these. So you can see very clearly that since it is monochloro, therefore it is having a density less than water, that is 0.89. For those who are unaware about this density of water, it is simply 1 gram ml. So it is the reference point. Water is taken as the reference point. So this monochloro has a kind of less density than this water. After that, we can see that all of these have a greater density than water, whether you talk about this dichloro compound or bromine or iodine, or you can say trichloro compound. So polychloro derivative and bromo and iodo all have a greater density than water, that is greater than 1. Now next is the solubility. Now solubility of haloalkane are slightly greater than this simple alkane. You know the reason very well. The reason lies in their polar nature. So if in order to dissolve this haloalkane in water, you have to need some energy, okay, to overcome the attraction between the haloalkane molecule and break the hydrogen bond between the water molecule. So if you want to dissolve something in water, then you have to break the bonds between your haloalkane molecules and break the hydrogen bonds between the water molecules. Therefore, a haloalkane can be inserted between them, or the required substance which you want to solute can be inserted between them. Okay. Now this would require less energy because new attraction will be set up between haloalkane and water, as these are not as strong as the original hydrogen bond, because original hydrogen bond includes a direct bonding of this oxygen and hydrogen, and oxygen is very electronegative, and we do not have a carbon type of thing there. Carbon decreases this, means the lengthening of this carbon chain decreases the solubility. So due to this result, the solubility of haloalkane in water is low. However, haloalkane tend to dissolve the organic solvent because the new intermolecular force of attraction between haloalkane and solvent molecule will have much the strength as the ones being broken in the separate haloalkane and solvent molecule. Okay, so this is about the solubility. So I would say that the solubility of haloalkane is greater than normal alkane, and its solubility decreases as we increase the length of this chain. Okay, this is clear. Now we'll start an introduction of this chemical reaction. Now chemical reactions can be broadly divided into three types. I would say broadly divided into three types. The first one is nucleophilic substitution. The second one is elimination, and the third one is reaction with metals. So today we will just see one of these, that is nucleophilic substitution. We will not go into all the details, we will cover it tomorrow. But for now, consider what is the meaning of all type of this reaction. So the first one is nucleophilic substitution. So you have to understand this term nucleophilic here. So nucleophilic means a nucleophile comes and attacks on a say target molecule and replaces that part, okay? Or you can say it get attracted to our electrophile. Now what is nucleophile? For those who are unaware about it, so nucleophile is something which is attracted towards your positive charge. So it should be having a negative charge with it, okay? And you know it very well that due to polarity of this CX bond, X has a partial negative charge. Say they can facilitate, and they also have a positive charge. So this presence of positive and negative charge, so now the positive center will provide the nucleophilic attack center because it is positively charged. So now nucleophile can attack and remove your X. You would say not X, it's halogen. Okay, so it is nucleophilic substitution. Next is our elimination reaction. Now what is elimination reaction? We are eliminating something from the molecule. So you must have heard that we have removed water from there. So that elimination, that dehydration is called as elimination. So it can be of any form. You can eliminate anything. You can eliminate this halogen. You can eliminate, say, our ketone, anything. Okay, water. So such type of reaction in which you are eliminating a part of the molecule, that are termed as elimination reaction. Now next is reaction with metals. So you will see the very important aspect of this when you will study this Grignard reagent. You will see there that for the preparation of this Grignard reagent, we have to do a reaction, that is reaction with metals. So these are the three types of reaction that you would encounter. So talking about the first one, the nucleophilic substitution. So in the nucleophilic substitution, what is happening here? Our electron-rich nucleophile will come and it will replace a leaving group in a substrate. Okay. Suppose we have CH3X. Now here the CX bond nature comes into role. Now all this say reactivity and all will now be decided on the base of the nature of CX bond, whether that CX bond is stronger or not, whether it has a positive charge center or not. So if you remember, I must have said earlier that this nature of CX bond is very important to understand that why some reaction goes in the way they go. Okay, so this is very important to understand our nature of CX bond, that this C is positively charged and this X is negatively charged, and as the size increases, the halogen size increases, the length increases, and your say this enthalpy also decreases. Okay, so if I talk about the types of nucleophilic substitution, and I would say this is the most hot topic of this chapter, that is SN1 and SN2 reaction. So let us get a clear picture of it in the next lecture. But for today, I will just give you a brief introduction for this SN1 and SN2. So in SN1, substitution nucleophilic unimolecular takes place. Now I want to make a point here that you must be aware about our rate law and all. What is rate law? What is first order of reaction? What is second order of reaction? So SN1 basically is a first order reaction, okay, and SN2 is a second order reaction. So by SN1 and SN2 we mean here that SN1 is a first order reaction and SN2 is a second order reaction. This is clear? Okay. Now what does this mean that SN1 is a first order? Means it only depends upon one of the reactant concentration raised to the power 1. Whereas in SN2, the biomolecular reaction, it depends upon two reactants individually. Okay. So both of the reactants contribute to our nucleophilic substitution reaction, SN2 reaction. So you have to consider both of them. So first let's look at this, what happens inside our substitution nucleophilic reaction. Okay, so in substitution nucleophilic reaction, what happens? First of all, it happens in two steps. Okay, SN1 is this SN1 reaction that occurs in two steps. So if you if you want to remember, then remember it like this, that this is SN1. So SN1 would give two steps and SN2 would give one step. So just opposite of each other. Did you get my point? So SN1 will give reaction in two steps and SN2 will give reaction in one step. As simple as that. Now what happens in this mechanism? So basically this mechanism takes part in mechanism goes in two parts. Okay, so this takes place in two parts. First, you will see the formation of carbocation intermediate. Okay, so remember all these points. We'll see it in more detail one by one. So remember these points just for now, so that, and if you want, you can try to read a bit of it. Okay, so first of all, there is a formation of intermediate between the this formation of intermediate by the departure of leaving group. Now this leaving group will also play a very important place in this chapter. Okay, now first of all, the formation of carbocation intermediate takes place and the leaving group departs. In the next step, what happens? In the next step, this nucleophile which we have discussed about, that has a either lone pair or negative charge, has a tendency to get attracted toward this positive charge. So they attack this thing, and where do they attack? They attack on the carbocation. Okay, so SN1 reaction may occur mainly in tertiary substrate and proceed via carbocation intermediate. So we'll see it, why it is happening fastly in this tertiary substrate. So for those who are aware about this hyperconjugation, well and good. If not, then also I will try to explain it. Okay, so just remember a little rule here, that more is the number of alpha hydrogen, more stable is our carbocation. Okay, simple as to see. More is the number of alpha hydrogen atom, more is the stability of the carbocation. Why is it so? It is due to our hyperconjugation. So this is partial shift of this, say, our sigma bond that is between carbon and hydrogen, to make this carbocation stable. Now what happens is that our nucleophile attack the carbocation and the reaction so we are there in the tertiary substrate. So therefore the tertiary substrate has a greater boiling point because it will have the max number of alpha hydrogen. Then we have the secondary, and then we have this tertiary primary. Okay, so this is the you can say order. So we'll see this order once again in the next class. Coming back to this SN2 reaction, that is substitution nucleophilic bimolecular reaction. The first one is unimolecular reaction and the second one is bimolecular reaction. So in this type of reaction, the reaction rate is dependent upon one thing. Okay, so we'll see all these things, on which thing it is dependent and on which thing it is not dependent. So for now next thing is this, in this mechanism only one step is occurring. So this reaction goes in one step. So the nucleophile attacks at the same time, simultaneously the leaving group leaves. So did you get my point here? This is the difference between SN1 and SN2. Now this SN1 sorry for the mistake here. This SN2 reaction occurs mainly in primary substrate. Okay, now this is the last point. So this is just opposite. Okay, this SN2 is just opposite of SN1. In SN1, you can say the tertiary one is more stable, and in SN2, this primary is the most stable carbocation. This is clear? Okay. So today we started with this halogen exchange. Then we look at the boiling points, physical properties. So let me make a quick brief overview of all of these. So first we'll start with boiling point. Now, two reasons are there due to which the haloalkane have greater boiling point than our normal alkane. What are the reasons? The first reason is the polarity of that bond. So this CX bond is polar in nature. Due to this reason, they have kind of have an advantage. Okay, so this is about our boiling point. Now compared to the haloalkane, they have no halogen or electronegative element present. Therefore, it will have a lower boiling point. Now the next is, since we have this halogens which have a greater molar mass, or we can say greater atomic mass, like our iodine, bromine, chlorine, they're very large in size. Now due to this reason, the intermolecular force increases and our say this boiling point also increases for haloalkane. Is this clear to you? Okay. Now next we move to density. Then we have seen that density of this polychloro, bromides and iodides, all of these three have this dichloro, or you can say polychloro, bromo and iodine. All of these have a greater density than water. Okay, this is clear. All have density less than greater than water except this thing, that is polychloro and our iodides and bromides. Then we have this, since we have done this density and boiling point, next we'll move to this our solubility. Now here also the solubility of haloalkane is greater than our normal alkane. The solubility of haloalkane is greater than our normal alkane. Why is it so? Because this haloalkane have again ionic character. Okay. Now we know very well that solubility of water increases as we increase the ionic character of the thing that is to be dissolved, because like dissolved in like, and water is also ionic in nature. So is this clear? Okay, this is clear. So with this I would try to end my lecture. So this was all for today.